quick recap. So if we have a conformal transformation, it means that there's a diffeomorphism such that g prime of x prime is equal to omega minus 2 of x, g mu nu of x prime. Infinitesimally, if we take x to x prime, which is x minus or x plus epsilon, then the action on operators, and I don't think I wrote this equation last time, so I wanted to get it in there. The action on operators is that O of x goes to O prime of x, which is e to the q of epsilon O of x, e to the minus q of epsilon. So q generates the infinitesimal transformation. You can exponentiate that and find the finite transformation on an operator. And I did write the following equation for the scalar primary. The scalar primary transforms with O prime of x is omega of x prime to the delta O of x prime. Yeah?
Why is there no I in the x prime? Are those q's anti-commission or something?
These are not, let's see.
Or does it have to do with the fact that we're Euclidean?
I don't know. Why should there be an I?
Well, if the q's were Hermitian, then we would need an I there in order for that transformation to be unitary.
Yeah. Maybe it's because we're in Euclidean. I'm not sure. I'm not sure. I'm using the conventions in the Simmons stuff and notes, which I posted. I suggested some reading in on the website. So I guess this is right in that convention. Okay, so this transformation rule, the statement is that correlators are invariant if you do this. So that gives you the rule on correlation functions, which looks like this. And I put in a box because I want to be able to refer back to it in a minute. Okay. Now, under dilatations, K mu, the special conformal generator, acts as a raising operator. Or sorry, other way. Lowering. Lowering operator. So acting with special conformal decreases the scaling dimension. And P mu acts as the raising operator. So what that means is that, and scaling dimensions can't go negative because that would give things that are not unitary, they would have negative norm. Because they can't go negative, so that means we can always act with the lowering operator until we get to a lowest weight state. That's the primary. By definition, it's something annihilated by the special conformal generators. And so then we can organize everything into lowest weight representations, where the lowest weight is the primary, and the rest of the representation consists of the descendant operators, which are what you get by hitting an operator with the momentum operator as many times as you like. And this just has the effect of putting in derivatives. So this is the derivative d mu1. Well, if you act on an operator, a scalar primary at the origin, this is just the derivative. Yeah.
I'm still confused, even if we're in Euclidean, right? Because I would think that we'd want these transformations to be unitary, so that they take like orthogonal states to orthogonal states if they're acting on the state instead of an operator. Or should I not really be thinking about Hilbert space unless we're in Lorentzian signature?
Well, these, I don't think these equations really care if you're in Lorentzian or Euclidean. I guess maybe they're anti-Hermitian. I'm not sure. I'm going to have to check the conventions on that.
Okay.
Or it's in the Simmons stuff and notes.
Well, certainly in the case of time evolution, in Euclidean signature, you have your time evolution operator is not unitary.
Yeah, that's right.
So
Yeah, I think that's just okay. I think that's just fine. Like when you evolve in Euclidean time, that's exactly the formula that you would write with the Hamiltonian there, and it's not unitary, and so what? It's fine. I think it's okay. Okay. So now I want to talk about Weyl transformations. Okay, so it's a fact that conformal field theories in flat space are also Weyl invariant in curve space. It's almost a fact. Okay, and we'll come back to the almost. But first, let me tell you what Weyl invariance is. Okay, so in a Weyl invariant theory, so the definition is that for any omega squared of x, the correlator O1 of x1, O2 of x2 dot 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 in the metric G is equal to omega of x1 to the delta 1, omega of x2 to the delta 2 dot dot dot, O1 of x1, O2 of x2 dot dot dot, omega squared G. Now, as I said over and over last time, this is not really symmetry, it's a transformation, okay? The theory on the left-hand side of this equation is in one metric, and the theory on the right-hand side is in a different metric. And there's no requirement that these manifolds, well, other than being related by this Weyl rescaling, there's no other requirement on these two manifolds. They don't have to be the same manifold at all, and we'll see examples where they're not. Now, if omega squared G mu nu is the same manifold as G mu nu, first of all, what do I mean by that? Well, I purposely didn't use a technical definition because I just mean the obvious thing, okay? I just mean, like, if this is the metric, if this is a metric on RD and this is also a metric on RD, then that's what I mean. And as far as formulas, this is exactly the statement that omega is one of the omegas that can be obtained by a conformal transformation. Okay, so in that situation, we can reinterpret the Weyl transformation law as a conformal transformation. So let's check. For example, let's look at a two-point function in flat space. So in the metric delta mu nu, dx mu, dx nu. The conformal transformation, or by a conformal transformation, let's do the conformal transformation with x prime equals lambda x. And we just use our conformal transformation law there. So this is lambda to the 2 delta O of lambda x, O of lambda y. Still in the flat metric because conformal transformations don't change the metric. But let's just, well, this is 2 points in the flat metric that have been rescaled by lambda, but we can just move this rescaling by lambda down into the metric. So this is lambda to the 2 delta O of x, O of y, in the metric lambda squared delta mu nu, dx mu, dx nu. And that agrees with our Weyl transformation rule over here. So this equality agrees with our Weyl transformation. Okay, and you can do the same thing for the other conformal transformations. Now, CFTs are Weyl invariant up to an anomaly because in curved space they obey an operator equation that says that the trace of the stress tensor is equal to a number, which is the anomaly. Okay, so on the left-hand side, this is an operator. On the right-hand side, this is number, C number, and it's the anomaly. And it's built, since it's just a number, it can only be built from background fields. In other words, the invariance of the background we're putting it in. So it's built from curvatures like R mu nu, etc. So this statement is proven in dimensions less than or equal to 10. I guess it's probably true in general. We're going to prove it in 2 dimensions later today. But first, let me just quickly explain why this gives you the Weyl transformation.
Tom?
Yeah.
Is there a state involved here?
Is there what?
A state.
No. It's an operator equation.
I see.
And that's why CFTs in curved space are basically as powerful as CFTs in flat space. It's not the expectation value of t that's set by the anomaly, it's the whole operator.
Unlike when you wrote it equals 0 before.
What? Yeah, just like when we wrote 0
Or
before.
just
Yeah.
like when-
Yeah, that was an operator. The trace being 0 is an operator statement for CFTs in flat space. The trace being a C number is an operator statement in curved space when you have an anomaly.
But you said that if you put it in an expectation value with other fields at the same point, then you won't get 0.
Yeah, that's the definition of the words operator equation. Are the definitions of those words are that it's true up to contact terms. Same here. This is an equation that's true up to contact terms. Okay, so how does that give us Weyl? Well, under changing the metric, g mu nu, to g mu nu times 1 plus 2 sigma of x, we can look at the partition function. We can vary the partition function under this. So we're just going to do a Weyl rescaling of the partition function. So infinitesimally, a Weyl rescaling just rescales the metric. So now we're going to see how that acts on the partition function. And by the definition of the stress tensor, this is the trace. Okay, so because we're rescaling the whole metric, so this is integral d dx root g t mu mu of x sigma of x. And now we can, okay, so using the anomaly, you can take this equation and use it to find z on a Weyl. You can find z on a different metric, which is related by a Weyl. Now that's not quite enough to prove our Weyl transformation law because I didn't insert any operators here. This is just the empty partition function. But we can repeat this argument with some operators inserted and get the Weyl transformation law.
What does that say after the delta on all transect these things?
Log z.
Log z.
So if we calculate the variation of a correlation function, we're going to get a similar equation, but now it's going to be integral d dx root g. We're going to get a trace t of x, and then we have an operator O of x1 dot dot dot. This is all in the metric g times sigma of x. Again, that's basically the definition of the stress tensor. It's the thing that comes down when you vary with respect to the metric. And now we see why it's important that operator equations have contact terms in them. Okay, so this has a contact term, which you're going to calculate on the homework. This has a contact term that's the scaling dimension times O times the delta function. And therefore we get a contribution delta sigma of x1, O of x1, dot, dot, dot. And then we get plus other contributions from other contact terms depending on what else appears in this correlation function. But the important thing is that this term here is the infinitesimal Weyl transformation. So we've just derived the infinitesimal version of the Weyl transformation law, which I guess I just erased. And there was no requirement here that I was doing a diffeomorphism. So there was no requirement that this was a conformal transformation. It was really a Weyl transformation. Okay, so that's Weyl infinitesimally, and then you can work harder and integrate it up and get the full Weyl transformation law. I'm now going to prove for you that conformal was Weyl in 2 dimensions. And in the process, we're going to derive the anomaly equation for 2-dimensional CFT. I'm going to mark this optional, okay? So the final result is not optional. But we're going to do some stuff here which is sort of tricky, and if you haven't seen CFTs before, maybe you should just relax for a minute and absorb some fun. Okay, so how does this go? So in flat space, T mu mu is equal to 0. And by the way, the reason I'm doing this is because I think this is a really beautiful method of argument. And we're not really going to use it later in this particular class. Like the tricks I'm about to show you, we're not really going to use later in this class. But they're very important for lots of stuff in CFT, and I think a really cool argument. Okay.
Tom?
Yeah.
So why is there a log there?
Where?
The log of the partition. Isn't it just the partition function?
The expectation value refers to no. It's 1 over z d by dz, right?
Partition function is like integral e to the minus s, and then if you vary that, then the action comes down, and then you get this with that.
I think you're thinking of the expectation value as being the path integral, but the expectation value is divided by z. The definition of expectation value is the path integral divided by z. Okay, well, if the trace is 0 in flat space, then let's follow the kind of effective field theory reasoning and write the most general trace that we could have in curved space. So if it's curved, the most general thing that we can write by dimensional analysis, let's write this up here, is T mu mu of x is minus c over 24 pi r of x. Let me write it first and I'll come back to it. Plus r o plus order grad to the 4. Okay, so r here is the curvature, is the scalar curvature of the background metric. O is an operator. Well, okay, so R is, so the stuff on the right-hand side has to be built from curvature invariance of the background. The only things that can show up there are curvature invariance of the background and operators. Okay, so we're just expanding in derivatives. Curvatures have 2 derivatives. they have dimension 2. Now, on the left, remember that T mu nu has dimension exactly equal to 2, or D in D dimensions. So the right-hand side also has to have dimension exactly equal to 2. So the first term already has the right dimensions. The prefactor here is just a constant, which is conventionally written this way. C is called the central charge. And for our purposes, I'm going to think of this equation as defining the central charge. I say it that way because the central charge shows up all over the place in two-dimensional CFT, and this is just one of many ways of defining it. I'll just define it to be this coefficient. Okay, so in the next term, R already has dimension 2, which means that O has to have dimension 0. Okay, so O has dimension 0. So that's kind of weird, and we're going to rule out that possibility, but for now we have to allow it. Now, at fourth order in derivatives, there's various things that you can write. You could write something like R squared, but R squared has the wrong dimensions. It has dimension 4, so you better put an O tilde in there with dimension -2. But there's no such thing as a negative dimension operator, so you can't. It's impossible to construct anything at fourth order that makes any sense, because you're always going to get 4 dimension 4 from the derivatives, and then you have to correct that with something with negative dimension, which doesn't exist. Okay, so we can ignore these terms, or they've been ruled out. Is there a question?
So you're thinking of O as like one of the primary fields in your CFT or something?
Yeah, let's see. I don't know if I've assumed it's primary, just some operator. Okay, now so we've narrowed it down to just these 2 terms, and I claim that the second term is impossible. We're now going to prove that. Now, one thing is that it's kind of weird to have an operator of dimension 0, but you can have, so CFTs can have operators of dimension 0. So, for example, the free boson in 2 dimensions, the X has dimension 0. Now X, it turns out, is not a good operator. It's not a normalizable operator in a way that I can come back to and explain later. But you can have operators that have dimension 0. So we need to rule this out, and we're going to use a fun trick to do that. So claim O equals 0. So that kind of looks like 0 equals 0. That's an O. The intuition for this is that if trace of t is related to an operator, then that means that the correlation functions of that operator have to be related in sort of a weird way to the metric variations. And we're going to show that there's just no consistent way to write down an effective action that has that property. So consider the object z of gj, which is the expectation value of e to the integral j of x O of x in the metric g. So we're not only turning on a metric, we're turning on a source for the operator O. Now we're going to vary. And I'm going to choose this variation in a way that it cancels off the two terms there. So the way of doing that is doing a variation where delta G mu nu is 2 sigma G mu nu, and delta J is sigma R. Now if we vary log z, this is integral d2x delta g mu nu d g mu nu plus delta j d dj log z. That's just a chain rule. Now, the metric variation gives a stress tensor expectation value, so this is going to give you a t mu nu, but the variation in the metric was sigma g mu nu, so that gives us a trace. And the other one, the variation gives you an O expectation value. The delta J we said was a sigma R. And so I've designed the coefficients here in such a way that they add up to just give the anomaly term using our trace formula. So we just get equals c over 24 pi integral d2x root g sigma of x r of x. Sorry, yeah, the anomaly. So far so good?
You want to put a negative sign there?
Where?
In the e to the negative j.
I don't know, do I?
If you look at that,
This actually gives a -1/2 of the stress tensor. So I think it works out correctly. I didn't include there's a coefficient here that works out. Okay, now what we want to do, so far there's no inconsistency, but what we want to do is we want to now vary again and show that there's an inconsistency at the nonlinear level. I'm going to do this in conformal gauge because it's good enough and easier. So conformal gauge means that we take our metric and we just write it as e to the 2 sigma times the flat metric. In conformal gauge, root GR is minus 2 box sigma, where box means d mu, d mu. So looking at our first, so now we're going to take the second variation of log z by acting on a first variation with another variation. And we get that immediately is delta sigma 1, delta sigma 2, log z is minus c over 12 pi integral d2x sigma 1 box sigma 2. Now for the tricky step, we're going to look at a commutator of 2 variations on log z. And this is 0 because we can just integrate by parts on this, on the 2 terms. So this is 0 by integration by parts. So now we look at what this commutator actually does on the background fields, just by doing the variation twice. So I'm not going to go through the algebra, but you just do the variation. We define the variation, you just do it again on the background fields. And what you'll find is that the commutator on the metric does nothing. The commutator on J gives 2 sigma 1 box sigma 2 minus sigma 2 box sigma 1. And this can be any function. So the conclusion is that if we vary log, if we do this variation this way, we're just doing a general variation with respect to J and getting 0. Well, if we do a general variation with respect to J and we get 0, then I guess log Z doesn't depend on J. Okay, so delta J log Z is therefore 0, and that means that we can take this operator O to be 0. Okay, conclusion. This stops being optional now. The conclusion is that in 2D, T mu mu is equal to minus C over 24 pi times R. Theory is not conformal in curved space. Trace is not 0, but it's conformal up to an anomaly, and that's really just as good. Yeah.
When you were arguing that there can't be fields with negative mass dimension, if I had a field with like mass dimension 1, and then I just did like the operator inverse of that thing, I would get something with mass dimension -1. Are these like...
There can't be local operators with negative mass dimension. Non-local operators can have negative dimension.
Okay.
The way you prove that, and I don't think I'm going to do this, I don't think I'm going to do this carefully, but the way you prove that is by looking at things like this and evaluating this. So this is a descent. You take some operator with negative dimension, you look at its descendants, and then you calculate, and you create, so this creates a state, and then you calculate the norm of that state. And I'm being pretty schematic here. I actually don't remember like which descendant you have to look at and everything, but there's some way of looking at the descendants and seeing that you can create states with norm delta, and therefore delta can't be negative. So it's a requirement of unitarity.
By a local operator, you mean one that satisfies, like, I mean, in Lorentzian, it would be like light cone, commutation relations and stuff.
Light cone? What does light cone have to do with it?
They commute outside of, they commute when they're not in each other's light cone.
Yeah, that's right.
That's what you mean by local.
Well, I'm working Euclidean, and local just means well, yeah, it means that the correlation functions are well defined on the well-defined functions of x. That's pretty much all it means. Like there are no branch cuts that would make it non-local, and that it's also its commutator vanishes in Euclidean unless you have coincident points. I guess while I'm at it, I might as well mention that if you do this in, like if you do this for a scalar operator in d dimensions, you find that delta has to be greater than or equal to whatever it is for a free scalar, which I can try to remember.
B minus 2.
Yeah, d over 2 minus 1. So a free scalar has dimension d over 2 minus 1, and the unitary, this is called the unitarity bound, and the unitarity bound for a scalar operator in CFT says that it has to have dimension bigger than that of a free field.
So are you saying that the free boson field is a non-local operator in that sense? Because I think its correlations are logarithmic. Right?
Yeah, the free boson is not a local operator.
Yeah.
Okay. So now I'm going to discuss the Weyl mapping to the cylinder, partly as an example to illustrate how to use Weyl, but also because this is an important application that we use all the time in CFT. So we want to take RD and map it by a Weyl transformation to R times SD minus 1. And that's pretty easy to do. We just take our metric on the plane. So that is, so by PL, I mean the plane, meaning Euclidean space. So the metric on the plane in polar coordinates is dr squared plus r squared d theta d minus 1 squared, where that's a coordinate on the sphere. Now we pull out the r. So there's a dr squared over r squared plus d theta minus 1 squared. And now I'm just gonna, that's actually, we're done. This is actually a cylinder. But let's write it in more cylinder-y coordinates. So this is e to the 2 tau, d tau squared plus d theta d minus 1 squared, where r is e to the tau. Okay, and this piece here is the metric on the cylinder. In pictures, it's pretty simple what we just did. We took Euclidean space, we took a bunch of spheres around the origin, and so R goes this way, and we just sort of blew them up into a cylinder. So the cylinder on the cylinder, these concentric spheres just become the slices on the cylinder, and in particular, so tau here goes up the cylinder, and in particular, so the radial direction on the plane becomes the Euclidean time. We're going to think of this as the Euclidean time direction. So the Euclidean time direction on the cylinder is the radial direction on the plane. In particular, the dilatation on the plane becomes just a time translation on the cylinder. So the dilatation r to lambda r becomes tau to tau plus log lambda, which is a time translation on the cylinder. This means that the dilatation operator d becomes the Hamiltonian h. It's actually not quite true. There's a contribution from the anomaly, which I may or may not come back to at some point. But this gives you a plus c over 12 in 2D. And similarly for the eigenvalues, so the eigenvalues of the dilatation operator are the scaling dimensions of the operators. So the scaling dimensions delta I become the energy levels EI. Plus the anomaly, which is plus c over 12. Sorry, did I get that right? Yes, okay. It's plus c over 12 in 2 dimensions. Let's calculate the 2-point function on the cylinder. This will be a good little practice problem. Using our Weyl transformations. We'll start by just writing the Euclidean correlator in polar coordinates. Okay, so we just want to rewrite the correlator on the plane. It's O of tau 1 N1 O of tau 2 N2, and I'll label it PL for plane. N is a point on the it's the angle. N is the angle. It's a point on the unit sphere. Okay, so this is just given by the usual 2-point function on the plane. The coordinate change is x is e to the tau n. And similarly for x2. Okay, because n is the point on the sphere, the unit sphere, and remember r is e to the tau. So this is just the usual change of polar coordinates. And now in that coordinate system, we know the answer. It's x1 minus x2 to the minus 2 delta. So I can plug in this coordinate change, and it's e to the 2 tau 1 plus e to the 2 tau 2 minus 2e to the tau 1 plus tau 2 n1 dot n2 to the minus delta. So that's just the distance squared in polar coordinates with r is e to the tau. Okay, we haven't done anything yet. We've just written the answer we already knew on the plane. We've just rewritten it in polar coordinates. Now we're going to do our Weyl transformation. The transformation that we're using is written right there, but let me write it in our usual Weyl notation. It says ds squared on the plane is equal to omega squared ds squared on the cylinder with omega equal e to the tau. So our Weyl transformation rule gives us this thing on the cylinder. So let's write down OO sil. That's the thing we're trying to calculate. According to our Weyl transformation rule, this is omega of x1 to the delta, omega of x2 to the delta, O of tau 1 n1, O of tau 2 n2 on the plane. So this gives you an e to the tau 1 and e to the tau 2. So the final answer is e to the delta tau 1 plus tau 2 times that thing that we had there, e to the 2 tau 1 plus e to the 2 tau 2 minus 2e tau 1 plus tau 2 and 1 dot n2 to the minus delta. Okay, I'm just going through this so you have a crisp example to look at. It's tricky to get everything in the right place, all the primes and the omegas, and it took me like 7 tries. But this is right. Let me tell you how I know it's right, because I literally mean it took me 7 tries. First of all, for n1 equals n2, so let's just put these at the same point on the cylinder, so they're only separated in time. Then this simplifies to 2 sinh of a half tau 1 minus tau 2 to the minus 2 delta. And if you now take tau 1 to tau 2, the cinch goes away, and the 1/2 and 2 go away. So this just becomes tau 1 minus tau 2 to the minus 2 delta, which you'll recognize as the answer on the plane. That's not a coincidence. So this is the proper distance to the minus 2 delta, and it always has to be that. No matter what transformations you're going through, if you go to short distances, it should again look like flat space. And the way the operators are normalized, we always normalize them to have unit coefficient here. Okay, so they're always normalized, well, not quite always. Usually always, they're normalized to have 1 times proper distance to the minus 2 delta. The reason we don't always do it that way is because sometimes we have a good reason to give an operator some other normalization. An example is the stress tensor. The stress tensor is defined by varying with respect to the metric, and that might not give you a 1 here, it could give you something else. So you don't just go rescaling it. The other thing, okay, so that's how I know I got the right answer. Okay, so the other thing I wanted to point out about the answer is that if tau 2 is much greater than tau 1, this decays exponentially. Right, the cinch becomes an exponential, so at late times this decays exponentially. Actually, I'm a little confused about that now. Did I calculate my distance correctly? Okay, I was thinking that was right, but that's kind of weirding me out. So, I mean, it's definitely supposed to decay exponentially mostly, but I'm a little confused, so I'm going to have to double check that I'm going to have to double check that and get back to you on that.
What are you confused about?
What?
What are you confused about?
Well, it's on a cylinder, and you're inserting some operator here on a cylinder, and it can go around the cylinder, so I'm confused why there's not a singularity after time 1. Oh, because it's a Euclidean cylinder. Sorry. Sorry. Okay, good. So Euclidean cylinder. Okay, let me back up a second. I'm not confused at all. It decays exponentially, as of course all correlators do on the Euclidean cylinder. The fact that it's exponential is related to the fact that the theory is gapped when you put it on the sphere. Right? So CFTs are gapless. CFTs on the plane are gapless. They have excitations all the way down to 0. But if you take a CFT and you put it on the sphere, it's now gapped. Its gap is the lowest energy, the dimension, which is the dimension of the first state. It's now gapped, and everything is going to decay exponentially. What I was confused about was the Lorentzian cylinder, but we're in Euclidean, so. went through that slowly and carefully to get the core to do everything using steps. But there's a shortcut to do this. That is to find this 2-point function, which is what people often use, which is just to define O of tau n to be e to the tau delta O of x equals e to the tau n. Sometimes when people are being friendly, they'll label these to show that they're different operators. That's O plane, and this is O sil. But more often, they'll just not care about you and won't label them. These are different operators. This is a definition. O plane is the usual operator we talk about. O sil is a new operator, which is defined this way. But people expect you to be able to figure it out by what arguments you put in. And then O sil tau 1 n1, O sil tau 2 n2, you can calculate just by substituting this definition, just by substitution. You just plug in the definition, and you get e to the tau 1 delta plus tau 2 delta O of x1, O of x2, which is exactly the answer we had earlier. I find this very confusing because O sil here, which is nicely labeled sil, is not on the cylinder. O sil is an operator on the plane. It's an operator in the CFT. Well, there's different ways of thinking about it. One way of thinking about it is that O sil is, both of these are in the flat. Both of these are in the flat metric, the plane metric. Okay, so O sil is an operator on the plane that mimics the physics on the cylinder. And sometimes people are thinking of it as actually being in the theory on the cylinder. Sometimes they're thinking of it as being in the theory on the plane, but like defined this way. And it gets very confusing. People always get the right answer, but the intermediate steps never make any sense. So I'm going to sort of try to be more careful and avoid confusing you like that, but this is what people do, and it's very confusing. Okay, questions?
So when you're calculating this correlator, it's a vacuum correlator in the according to the vacuum on the plane or on the cylinder?
This one?
Yeah, this one or the other one.
Oh, good. The answer is that the answer is both. Okay, so when we do the let me try to answer that more carefully.
Can we just think that in one case you're changing the vacuum but keeping the operator same, in the other case you're changing the operator but keeping the vacuum same?
I would, well, put it this way. I think the theory on the plane and the theory on the cylinder are two different theories.
Yeah.
Like, they're in different metrics and stuff. Now they're related by Weyl, and that's why people are able to get away with being sloppy about this. But I like to know what theory I'm working in, and you're not just changing the vacuum state, you're changing the theory. It's not a different state in the same theory. Okay, so let me try to address your question of which vacuum we're in and everything. So when I write a correlator on the plane, one way I can think about that is that this is defined by doing the path integral on the plane with some operators inserted. Now, as we've discussed, doing the path integral on the Euclidean plane does calculate stuff in the Minkowski vacuum state. Okay, because we can reinterpret this in operator language as calculating this correlator in the Minkowski vacuum. When I write ... sil, I mean the path integral on the cylinder with my operators inserted. But again, this path integral on the cylinder calculates correlation functions in the Minkowski vacuum of the cylinder. Okay, so they're both in the vacuum state. This one is in the Minkowski vacuum of, we could call this the vacuum of Rd minus 1, because that's space. And this is the vacuum of Sd minus 1. Yeah. This is actually not how we usually interpret this. You can interpret it this way. But what we usually do is to interpret correlators on the plane using the cylinder. Okay, let me say that again. Okay, so the point is there's two different ways of slicing this path integral. So, and they have to be equal. You know, you can take a path integral and chop it up however you want, but it'll give the same answer. We could chop it up this way, and then we're talking about states on the line being evolved with the translation operator in that direction, that translation operator. That's one way of thinking about it. That would be the right way to think about it if we were thinking about our theory in Minkowski space and thinking about the Minkowski vacuum state. This would prepare the Minkowski vacuum at time 0. A different thing we can do is we can go to the cylinder and chop things up in a way that's sort of natural on a cylinder. So now we're thinking about states which are in the sphere vacuum, states which are in the sphere vacuum and then evolved using the time translation on the cylinder. But another thing we could do is we can use this set of states in this picture. Okay, so we can think about the theory, think about space as the spheres, but we don't have to go to the cylinder to do that. We can just chop the path integral up this way. Because these concentric spheres rather, correspond to the fixed time slices on the cylinder. This is called radial quantization. And usually in CFT, well, at least in 2D CFT, it varies in higher dimensions. But often in CFT, when we take one of these things and we translate it into like Bras and Ketz, we're working in radial quantization, which is just another way of saying that we're kind of thinking on the cylinder but working on the plane. Yeah.
I mean, in that diagram you drew on the top, you also have to reinterpret where the bra is and where the ket is.
That's right. Yeah. So I'm going to write a couple equations for that.
Ket is at the origin in the plane, right?
That's right. Okay, and this is part of what's called the state operator correspondence. So, in any quantum field theory, local operators, or a local operator, gives you a state on the sphere SD minus 1. This is a consequence of all of our discussion of path integrals, because we can define that state as follows. So for an operator O of x, corresponding to an operator O of x, we define a state, ket O, which is the path integral with the operator O inserted at the origin, and then you do the path integral inside the ball. Okay, so this is a ball. Its boundary is SD minus 1. And recall that the path integral defines a quantum state on SD minus 1. So this is a quantum state. You can do this in any quantum field theory.
Acting with the operator O on the vacuum state of.
Yeah, so the way we think about it is that you can define a vacuum state. Well, you can define a vacuum state to be the state with no operator. But in a general quantum field theory, this will not be. In a general quantum field theory, this will not be the same vacuum state like that you would. This will not be the vacuum state. Let's just call. I won't call it the vacuum. Let's call it V for wants to be vacuum. This will just give you some state.
But doesn't the picture correspond to like evolving in imaginary time in the radial direction for an infinite amount of time, and then that should bring me to the vacuum state?
It's not infinite.
Oh, you put the boundary at a finite radius or something?
Are you talking about the cylinder? Are you talking? I mean, this is not an infinite amount of time. This is 0 to R.
I see.
Okay, so that's why I don't think in general it's going to put you in the vacuum.
I was imagining that was really big.
Then I guess it would. Okay, I'm really not sure if it would or not. But if the theory is conformal, this actually is the vacuum state, and that's where I'm going in a minute. Okay. So in a conformal field theory, two things happen that are nice. So first of all, the Hilbert space on SD minus 1 is independent of radius. Like, it doesn't matter where we draw the ball. We can just do dilatations to get a very easy mapping to other radii of the ball. So we just set this to 1, usually. So let's just set that to 1. And the other nice thing that happens in CFT is that any state can be used to define a local operator.
So that means that our cylinder also has a height 1 or something?
We haven't gotten to the cylinder yet, but here I was talking about a quantum field theory, and there is no mapping to the cylinder in a general quantum field theory.
Okay.
That's only in CFT.
Right, but now in CFT you're setting the radius to 1. Or sorry, that's the.
Yeah, that's
the
times
radius of
0.
the Circle.
So radius equals 1 on the plane is time equals 0 on the cylinder. Right? R is e to the tau.
Okay.
So,
Got
okay,
it.
so in any QFT, a local operator can be used to give you a state. But what's special about CFT, one thing special about CFT is that a state gives you an operator.
So the cylinder is going to
And-
be like infinite downwards, but.
Yeah, let me get to that. And the reason for this is that you can take your, so let's take a state, psi, defined on the sphere. And in CFT, we can use dilatations to shrink it down to a point and insert it into a path integral somewhere. Like if we have some path integral with some other stuff out here, then we can use dilatations to shrink this down, and it now lives at a point. We can define a local operator by inserting this state at a point into a path integral. Okay, so the point is that it's 1-to-1 in CFT. There's a 1-to-1 correspondence between states and local operators. This is not true in general. This is not true in ordinary, regular quantum field theories. Okay, let's stop there for today.
This seems to suggest that whenever there are operators, I need to like remove spheres around them and then like this contract this path integral to spheres around those operators.
What?
So I'm saying if you have, if you want to show the state is related to like correlation function of operators or something.
Uh-huh.
So how would you do that?
We would define the correlation functions of that operator
Okay.
by inserting this state into the path integral on a little teeny circle. So like, you know, oh, if we had a state, if you gave me a state psi, then I would find an operator O, and I would define its correlation functions to be whatever the other stuff is, and then you put a little tiny circle here with the state psi inserted on it. What do I mean to insert the state on a what I mean by that is that you have to use the wave function and integrate against that wave function. I can show you a formula, but let people go.
But if like the operators are coming arbitrarily close or something.
If what if you
If
mean
the-
other operators are coming?
Yeah, arbitrarily close. You have to like.
Well, we only have to know how to insert this away from other operators. The definition of an operator is there's ambiguities if you put it on top of other operators. We're only defining this operator away from other operators.